The rivet comes out of the coke fire at 1,100 degrees Fahrenheit. It is the color of a dying sun, orange fading to white at its crown, and it lives in that state for approximately 11 seconds. In those 11 seconds, four men must perform a sequence so rehearsed, so brutally precise, that a single miscalculation means a compound fracture, a crushed eye socket, or a rivet embedded in a man's forearm like a brand. The catcher, youngest of the gang, usually no older than 16, takes it from the heater in a leather cone and pitches it upward into the hollow of the boiler shell. 12 feet, sometimes 18. The holder-on receives it through a hole the width of a fist, jams it flush against the iron plate with a dolly bar, and leans his entire body weight into it. The riveters on the outside, two of them, alternating hammers, begin driving. The sound is not a clang. It is not a ring. It is a concussive, skull-compressing crack that repeats at a rate of 40 blows per minute across a shop floor where 200 such operations occur simultaneously. In the Lancashire boiler works of 1860, the noise was measured, by those who thought to measure such things, at levels we now classify as permanently deafening after 4 hours of continuous exposure. Most men worked 10-hour shifts, 6 days a week. For decades, they went home unable to hear their children speak. They went home with iron scale embedded beneath their fingernails, in the creases of their necks, in the corners of their eyes. They went home to houses that shook when the nearby mills ran night shifts, and they did not notice, because they could no longer feel the difference between vibration and silence. The boiler fed the empire. The riveter fed the boiler. Nobody asked what fed the riveter. The boiler was the most important machine the 19th century ever built. It powered the looms. It drove the locomotives. It pressurized the mines, the ships, the ironworks, the municipal waterworks of every major city from Manchester to Bombay. Without the boiler, the Industrial Revolution was not delayed. It does not begin. Steam was not a convenience. It was the operating principle of an entire civilization. And yet the boiler was, by its essential nature, a vessel designed to contain forces it could not permanently withstand. Every boiler ever built was in a state of slow negotiation with its own destruction. The pressure inside pushed outward, always, against the plates, against the seams, against the 10,000 rivets hammered by men whose names no ledger preserved. The question was never whether a boiler would fail. The question was when, and who would be standing closest when it did. This is the story of the men who built the box, and the box that consumed them. Between 1850 and 1900, boiler explosions killed more industrial workers in Britain and the United States than any other single category of mechanical failure. The numbers are not approximate. The Manchester Steam Users Association, founded in 1855 specifically to investigate boiler disasters, recorded 10,000 explosions across Britain in the second half of the 19th century. In the United States, the Supervising Inspector General of Steam Vessels reported that between 1816 and 1848, steamboat boiler explosions alone killed at least 2,300 people on the inland rivers, and those were only the incidents large enough to generate federal documentation. The true figure, accounting for factory boilers, mill boilers, and the uncounted dead in provincial works where no inspector ever set foot, is substantially higher. The explosions were not accidents in the way a loose cobblestone is an accident. They were the predictable result of a system that demanded maximum pressure, minimum expenditure, and zero tolerance for production downtime. Boiler inspections were voluntary in Britain until 1882. In many American states, they remained effectively unenforceable for decades beyond that. The men who built the boilers knew this. The men who owned them knew it also. Only one group bore the consequence. The Lancashire boiler was patented in 1844 by William Fairbairn and John Hetherington, two men whose names appear in engineering histories, in bronze, on institutional plaques. The boiler itself was an evolution of earlier fire tube designs, But the Lancashire configuration was specific and deliberate. A large cylindrical shell, typically 8 feet in diameter and 28 feet in length, housing 2 internal flue tubes through which furnace gases traveled before exhausting through the rear. The geometry concentrated heat efficiently. It produced sustained, reliable pressure. It was scalable. Mills adopted it immediately. Breweries, dye works, paper mills, municipal pumping stations. By 1860, the Lancashire boiler was the industrial standard across the British North. Manufacturing one required between 8,000 and 12,000 individual rivets, depending on shell diameter and working pressure rating. Each rivet was driven by hand. Each joint was the product of a four-man gang working in sequence, in heat, in noise that precluded any communication beyond gesture and long practice. The engineering journals of the period celebrated the boiler's efficiency with columns of precise data: pounds per square inch, thermal output, fuel consumption ratios. They did not calculate the cost in hearing, in lung tissue, in years of functional life per operative. That arithmetic was performed elsewhere, in silence, in the bodies of the men themselves. The rivet joint was not a simple fastening. It was a calculated act of controlled deformation. A hole was punched or drilled through 2 overlapping iron plates, the shell courses of the boiler barrel. The rivet, a cylindrical shank of wrought iron with a preformed head at one end, was heated until plastic and inserted through the aligned holes. The holder-on pressed his dolly bar against the preformed head with the full resistance of his body. The outside riveters then drove the protruding shank, spreading and mushrooming its tail, into a second head that clamped the plates together as the iron cooled and contracted. The contraction itself generated the clamping force. The joint's integrity depended entirely on that final compression, on the temperature at which the rivet was driven, on the uniformity of the blows, on the concentricity of the hole, on the flatness of the plate surfaces meeting beneath. Any deviation in any variable produced a joint that looked sound and was not. A rivet driven too cool did not fully consolidate. A hole punched rather than drilled left microfractures in the surrounding plate. A lap joint subjected to cyclical pressure flexed minutely with every firing cycle, thousands of times per year, and the iron at the rivet hole edge began, invisibly, to crack. The boiler did not announce this process. It continued producing steam. It continued driving machinery. It continued, in every observable sense, to function until the accumulated damage reached the threshold beyond which iron plate offers no further negotiation. The most dangerous boiler was not the neglected one. It was the one that had run without incident for 11 years. Longevity bred confidence. Confidence bred reduced inspection intervals, deferred maintenance. Incremental pressure increases as mill owners pushed output to meet contracts. A boiler rated at 60 pounds per square inch in 1858 might be operating at 80 by 1869, the adjustment made not through formal reclassification, but through the slow, undocumented creep of a pressure gauge needle that nobody chose to question. The internal flue tubes were the critical vulnerability. Subject to external water pressure on one side and furnace gas temperatures exceeding 700 degrees Fahrenheit on the other, they were susceptible to a failure mode called collapse. An inward buckling that could occur with no external warning, rupturing the shell and releasing the entire water content of the boiler as a near-instantaneous flash of steam. A boiler containing 1,000 gallons of water at operating pressure did not leak when it failed. It detonated. The force was equivalent, in the investigations that followed the larger disasters, to several hundred pounds of black powder. The boiler house did not collapse. It ceased to exist as a defined structure. And the men inside it, the stokers, the rivet inspectors, the maintenance workers conducting their ordinary morning rounds, ceased with it. A riveting gang was not assigned. It was assembled over years, through proximity and survival. The heater boy entered the trade at 13 or 14, drawn from the same streets that fed the mills and the foundries and the coal staiths. He learned to read the color of iron in a coke fire the way a baker reads bread. By shade, by duration, by a judgment that lived in the eye before it ever reached the mind. By 17, if he had not lost fingers to a misdirected toss or a dropped cone, he might advance to hold her on. By his mid-20s, if his hearing held and his grip remained, he might drive. The gang developed a communication system built entirely from rhythm. The pattern of hammer blows conveyed information that voices could not carry across the noise. 2 rapid strikes meant reposition. 3 slow meant the rivet was cooling too fast. A single heavy blow meant stop. They ate together at the base of the boiler shell during the 20-minute midday break. Bread, cold dripping, occasionally a piece of boiled bacon wrapped in cloth. They ate in the same posture they worked, crouched, shoulders forward, arms carrying the permanent set of men who had spent years resisting force. Their average working life in the trade was 19 years. Their average lifespan was 51. On the morning of June 2, 1882, the Farnworth boiler house of the Jubilee Cotton Mill, Bolton, ceased to exist in 4 seconds. The number 3 Lancashire boiler, 11 years in service, last formally inspected 22 months prior, operating at an estimated 84 pounds per square inch against a rated maximum of 65, suffered complete flue tube collapse at 6:47 in the morning, 14 minutes after the first firing of the day's shift. The shell separated at the rear longitudinal seam. Investigators found the primary rivet line had been failing incrementally along a 4-foot section for an estimated period of 18 months. The individual rivets had not sheared. The plate itself had torn, a distinction that told engineers precisely what it told them about the quality of iron used in the original shell courses. The boiler traveled 47 yards before it came to rest against the outer mill wall. 7 men died immediately. 3 more died within the following week from scalding. The stoker whose ordinary duty placed him 6 feet from the rear of the boiler at that hour was identified by his belt buckle. The inquest lasted 3 days. The mill resumed production within 11. At the resumed inquest hearing, the mill owner stated that no inspector had ever formally condemned the vessel. He was correct. The Boiler Explosions Act of 1882 passed the British Parliament 4 months after Farnworth. It was not the first such legislation attempted. Bills had been drafted in 1865, in 1871, in 1878, each defeated or diluted by industrial lobby pressure that argued mandatory inspection would constitute unlawful interference with private property and commercial operation. The 1882 Act passed not because the calculus of industrial power had shifted, but because the accumulation of documented disasters had finally exceeded the threshold of what parliamentary silence could absorb. The Act required periodic inspection of boilers in factories and workshops. It did not specify minimum intervals. It did not establish a centralized inspectorate with enforcement authority. It did not mandate the retirement of vessels beyond a defined service age. In the United States, federal boiler regulation remained fragmented across state jurisdictions until 1911, when the American Society of Mechanical Engineers published the first edition of the Boiler and Pressure Vessel Code. Itself prompted not by legislative will, but by an explosion in a shoe factory in Brockton, Massachusetts, that killed 58 people and injured 117 more. Reform followed disaster. It did not precede it. The last hand-riveted boiler in commercial British service was decommissioned in 1962. By then, welding had replaced riveting as the primary method of pressure vessel construction. A transition driven not by the welfare of riveting gangs, but by the superior consistency of a mechanized process and the economics of a labor market altered by 2 world wars. The men who built the boilers left no monuments. The trade journals that chronicled the Lancashire boiler's engineering refinements across 90 years devoted, in total, fewer than 4 pages to the mortality rates of the men who fabricated them. The explosion inquests are preserved in regional archives, their language measured and procedural, their conclusions almost uniformly the same. Insufficient inspection, excessive pressure, no criminal liability established. The boiler fed the century. The riveter fed the boiler. In the end, what sustained the entire architecture of industrial civilization was not iron, nor steam, nor the genius of engineers whose names are carved in stone. It was the 11 seconds between the fire and the hammer, and the men who lived inside them.